Welcome back. So this is video 2 on statistical independence, testing whether or not two events are independent. In video 1 we looked at what that idea actually means and we looked at some examples, and I suggest you watch that one first if you've not heard of this stuff before, and then it'll make more sense. So a summary of what we found in that was that if two events are independent, it means that the event that one has occurred does not alter the probability of the other occurring. The example we used was coins and dice. If I throw a die and it's a pair 6-faced die and I say, what's the probability I roll a 3? You would tell me 1 in 6. If I then tell you, oh, I just flipped a coin and got a tail, you would still tell me the chance of getting a 3 on the dice is 1 in 6. Because the result of my coin toss is independent of the result of my dice throw. That's what independent means. Not independent would be something like, if you're a year 13, the events having a job and owning a car. Not independent because if I know you have a job, it increases the probability that you have a car because you've got money to play with. Okay, so that was what we talked about. In this one we're going to do an example. Exercise 4. This is all about house selling prices. So basically we're looking at how long they were on the market before someone bought them and the price they sold for. Question 1. C is the event that a house sold for under $300,000. So that's C. Think C for cheap because it's the cheapest ones. F is the event that the sale was made in less than 30 days. So think F for fast. It sold fast. The question is, are events C, cheap, and F, fast, statistically independent or not? So this is how we tell. We compare the probability of a randomly chosen house being cheap, so that's 85 out of 181, with the probability of a randomly chosen fast house being cheap, which would be 39 out of 82. So we've got to compare those two probabilities. All right. So if the probability of C is the same as the probability of C given F, in other words, knowing that it sold fast doesn't change its probability of being cheap. If that's the case, then we can say they're independent. However, if that's not the case, if those probabilities are different, then we have to say they're not independent. So the equals with a line through it means not equal to. So if they're not the same, then they're not independent. And that's the rules you use. Okay, so I'd like you to write down the probability of each of those things. So the probability of C and the probability of C given F. And I want you to work them out as decimals and compare them. So pause the video and do that, please, and hit play once you've had a go. So the probability of C, that's the proportion that are cheap, that's going to be 85 out of 181, which as a decimal equals 0.4696. Now, what do we want to compare it with? Well, if they're independent, then that probability will be the same as the probability of C given that F occurs. So let's work that out. Pause the video and do it if you haven't had a go yet. So the probability of C given F means out of F, so out of the houses that sold fast, which is the left column, out of 82, 39 of them were cheap. So 39 of them were under $300,000. And again, we need to work that out as a decimal so we can compare it. 39 divided by 82, and that is 0.4756. Now, are those two probabilities the same? So we can only call them statistically independent if they're the same. They're not. They're slightly different. 4696 compared to 0.4756. So they're different, which means that events C and F are not statistically independent. And the evidence for that is probability of C is different to the probability of C given F. That's what you'd need to write in an exam at this level. In reality, so if you were asked to actually maybe comment further on this and show some insight, in reality, what do you notice about those two numbers? I mean, one's a smidgen under 47%. The other is just over 47%. They're pretty similar, aren't they? Now, we've only got a sample of houses, and so in reality, that difference is probably not meaningful in practice. It's probably not something that I'd read into. A difference as small as that, 46.96% to 47.56%, a difference that small could just be due to the sample of houses we happen to get. And if we took another sample, it might be the other way around. So actually, in practice, we wouldn't draw any conclusions from that difference. It's too small. So we would end up saying, well, in reality, we can't really tell whether or not those two events are independent based on this evidence. It's too close to call. I'd only say that in an exam if they asked you to comment further on it. The short answer is, at achieved and merit level, they're not independent because the numbers are different. It's the short answer. Question 2. Recall E is the event that a house sold for over 600,000 and H is the event that the sale was made in more than 90 days. Are those two events independent? Well, I'd like you to have a go at this question, and when you're ready, hit play and see how you go. So, the events we need to look at. So, we need to find out the probability of E. Think E for expensive. So, probability, if we pick one of those 181 houses at random, the chance that it's an expensive one is 12 out of 181. Or about 6 and a bit percent. And if we want to know if it's independent of event event H, then we need to calculate the probability of E given H and compare it and see if it's the same or not. So E given H, so that means it's out of the houses that sold for more than 90 days only, so it's out of 19. And how many of them were expensive? 0. So actually 0 chance. If we pick from this particular group of houses, there's none of them that would fit that category. So the probabilities, are they the same? No, they're not. Probability of E is not equal to the probability of E given H. So no, events E and H are not independent based on this evidence. Okay, the next thing is some discussion, a discussion exercise, and it's going to lead us to another way of testing for independence, which is actually faster, but makes a little bit less sense until you've seen it in action. So this is the discussion exercise. So for any events A and B, we've talked about how earlier on there's the conditional probability formula. The probability that A happens given that B happens means it's out of the B event. We know that's occurred. And when we look at an example of that, if we wanted to know the probability that a house sold for under 300,000, given that it sold in less than 30 days, then it would be 39 out of 82. The 39 is actually the intersection of under 300,000 in less than 30 days. So it's where they both occur. So the numerator in this formula is going to be the probability of the intersection of A and B both occurring. The denominator is going to be the probability of what it's out of. So like the 82 out of 181, that would be the denominator. So given that a house sells for less than 30 days. So the probability of A given that B occurs equals the probability of both A and B occurring divided by the probability of B. That's our formula for conditional probability. If A and B are independent events, then we know that the occurrence of event B doesn't change the probability of A happening. So we get the statement here. If independent, then probability of A given B is the same as the probability of A. So putting these two formulae together, the probability of A given B, so that's the left-hand side, can be written as this, can't it? So let's do that. So that's the probability of A and B divided by the probability of B. And if they're independent, then that equals the probability of A, doesn't it? Now, that means that if we were to make this event the probability of A and B both happening, if we were to make that the subject of that formula, how would we do that? Well, we'd need to multiply both sides by the probability of B. Wouldn't we? So multiply both sides by the probability of B, and we get probability of A and B equals the probability of A times this, so times the probability of B. And that leads us to a faster, simpler way of testing for independence. That is, if A and B are independent events, then the probability of A and B is going to be equal to the probability of A times the probability of B. If that formula doesn't work, in other words, if multiplying the probabilities of A and B doesn't give you probability of A and B, then it means the events are not independent. Alright, test that formula out on question 1 or 2 and see if it gives you the same conclusion, which is that they're not independent. The next page, question 1, I'm just going to get us started on that, and it's just about linking what we've been learning back to Venn diagrams and tables. So take two events, A and B. Event A occurs 65% of the time, so let's fill that in. So A is 65% of the time, or 0.65, 65%. Event B occurs 32% of the time, so 32%. The totals have to add up to 100%, we know that. And 25% of the time neither of them occurs, so not A and not B, 25% of the time. So pause this video and fill in the rest of the table, please. Hit play when you've done that. Okay, and there we have it. Now, we're going to now transfer this onto a Venn diagram. This is our Venn diagram, goes on the right here. The thing about a Venn diagram is it's just another visual way of representing this. And the way it works is if you take event A, and we'll colour event A red. So here's event A. And we'll colour event B, we'll colour it green. And sorry, this will be awkward if you're colourblind. But so what I've done is I've circled those two events. And on a Venn diagram, it's the same idea, except we don't have all the numbers. Initially we just have the shapes, and we use circles. So event A is going to be red, like so, and event B is going to be green. Look at my beautiful circle, like so. And the zone where they overlap, remember, what do we call that? Well, we call that the intersection of the two events. So that's the intersection. We call it A and B, so intersection. And on a Venn diagram, you can see it's the same as basically what it is on the table. Again, it's the overlap point, so that's the 22% one. So this one's A and not B, the one I've just drawn in. What's this one going to be? Well, it's going to be not A and B. So it's B, but it's not A. And what about the region outside of the circles? So that's the no-no. That's your not A and your not B as well. 25% on the bottom right of our table. So we say that's not A and not B. And we could write those probabilities in. The probability of the intersection of both A and B is 22%. So that would be either decimal 0.22. And the probability of A but not B, that would be 43%, so 0.43, etc. Okay, and you can do the rest. Now, some special terminology. The area of the frame containing a Venn diagram, so that's the set of all possible outcomes that could occur, the whole shebang. That represents what we call our sample space. So the word that goes up here is sample space. And it represents the set of all possible outcomes. And you always need to draw that frame in. If you don't draw the frame, it looks like there's no way of getting the no-no event. Okay, now to get the answers to the following questions, you can look up the answers on the OneNote, but hopefully this has given you the general idea. Question B is really important, question B and C actually, because it will really help you get comfortable, hopefully, and get you comfortable with the link between the notation and the maths, and also the probabilities and the idea of what's actually going on here. So I think it's very important that you do this this exercise, and I promise you that if you do it and you make sense of it, the stuff will start to become a lot easier. You want to get to the stage where it's so easy it's kind of boring, because when you get to your exam, they won't ask you questions like in this form. They'll be in a context. And when I say in a context, I mean like the sort of questions we can see down here. And you need to be able to go from the context to the notation in the diagram. You need to be able to link those things together. So practice is key. All the best.